So I think we should start. We have prepared, I think, plenty of slides for the time given. And yeah, should we head over?
Yeah, ready when you are.
Yeah, well, let's go to, yeah. So from this point, welcome to the Elektor webinar, Microcontrollers Pixel Artist. So we will talk about generating video moving pixels, sprites, and tiles. And this is addition, add-on, or short summary of the article in the current January edition of Elektor, where the main article is Microcontroller as Pixel Artist. I think the title is a little bit different, but that was the working title for that. And yeah, you may see a well-known face and maybe a new face to this format. Today with me, my name is Mathias Claussen, and we have also with me Brian Tristam Williams. And yeah, Brian, may you like to introduce yourself a little bit so that the audience...
Sure. I was buying my first Elektor magazine when I was about 16 years old, so that was maybe 3 years ago. And funnily enough, it was a video-related article. So I've always been interested in video because back in the day, we had PAL and we had NTSC and we had NTSC Laserdiscs and only PAL TVs, and multi-system was very expensive. So Elektor had a lovely little circuit that could convert PAL to RGB. And I've been following Elektor ever since and working with you guys full-time for maybe 6 months.
Yeah, and to those who wonder why you don't have the same background as behind me, you are not sitting in the same office, so...
No, it was quite a walk to get to, so I decided to stay here in Johannesburg, South Africa.
Yeah, but at least you're in the same time zone, so that helps a lot.
We're in the same time zone 6 months of the year. Right now, I'm an hour later than you. Yeah. Excuse the way I'm talking, I've got an echo in my headset. I'm hearing myself.
Oh, that's not intended. Yeah, but you are going into summertime. Or you are in summertime, sort of.
We are in summer.
Yeah.
Spring will come up for you and autumn for us.
Yeah. Let's see. Yeah.
So if you do see me sweating, it's 25 degrees in here, and I won't put the air conditioning on because it will interfere with our lovely audio.
Yeah, this morning we had lovely 2 degrees in the morning, or even below that. So it's a little bit colder here. So you don't need an echo, but yeah. So back to the slides. So yeah, we have introduced ourselves, so you know who your today's hosts are. You should know me from the few last webinars that have been passed already. And yeah, what are we going to do today? So what will be covered? We have an introduction in some classic hardware when it comes to video generation, so that you get an idea of what sort of stuff we are talking. A small background about video signals. We will show you how to get composite video with an AVR on Arduino. We will talk about VGA with an ESP32 and a Raspberry Pi Pico, and DVI with the Raspberry Pi Pico, so for the video output section. And we will talk about sprites, tiles, and Mode 7 style graphics. And to those who don't know what Mode 7 style graphics is, you will see a live demonstration later for that. Brian, you prepared some classic
yes, indeed.
hardware.
I've been doing this for a while, and I could go back to the Z80, which was one of the 1970s microprocessors, not even microcontroller, microprocessor. And back in those days, the only thing you had was your television in your house. They did make terminals that could show pictures, but those things, you could buy a car for the price you paid for one of those. So this is how you learned assembly, late 70s, early 80s. No monitor, but a little keyboard. And you had to assemble the code for the microcontroller with pencil and paper. I've done that. And then punch the hex digits in and your display was this wonderful 6-digit 7-segment display. So as I said, a terminal with a custom screen was hellishly expensive, and they decided if they want to get the stuff into the home, maybe use the screen that's already there if you want to make things like this possible. Now, unfortunately, this is a recent acquisition. I wasn't as lucky as you to have one of these when I was a kid, but I was a Texas Instruments guy. So I had one of these. Now, to get these working, you needed a special chip called a CRT controller, or a video display processor in Texas Instruments words. And, you know, they had all kinds of hardware and books on them on how to generate the characters. And that's great, but this is a 42-year-old machine. We have since advanced to things like Arduino, but they don't have video output. If we take a look inside here, you can see this big baby here is the microprocessor. It has RAM and ROM connected, but this entire section here is analog video output, the video chip, and 16 kilobytes of RAM. So I'm thinking with an Arduino running at 16 megahertz and this thing only running at 3, maybe we could modernize the CPU and use the old hardware. So if we go back to the slide there, please, Mr. Producer. If you go to the schematic diagram, a couple of slides ahead. Yeah, that one. So this is an example architecture for the TMS9918. It's a popular chip. While it was in the Texas Instruments computer, it was also used in the MSX architecture at 256 by 192 and up to 16 kilobytes of RAM. And this particular picture that you're looking at is the architecture for the Texas Instruments, the video output, the section I showed you before. And if you look at it, it's got an 8-bit bus on the left and like 4 control signals that are necessary. So that's fully Arduino compatible. And while you'd be a far cry from being able to do stuff like that at that speed, running on pure assembly in Arduino, it is replicable at least. So here's a board, that same processor, the analog output circuitry, and 16 kilobytes of RAM connected to an Arduino. So you can do demonstrations like that. But is that practical? No, of course not. I don't think you're going to hook all that up to your Arduino just because you want a CRT display for your temperature monitoring or your soil watering. So instead, later on came options such as build a little PIC circuit with a composite video output and a switch on and off. And sorry, I was on the wrong camera. I never got this to work. Would have been cool, but I'm not as talented as Mathias, who will show us how to do that sort of thing. From the Arduino, you can get black and white video. Let's see what you've got. What hardware will you show us today?
So let's switch back camera and microphone on. Yeah, I prepared a slide for that. So let's go to that position. What we are using today is an Arduino Uno. It's quite simple to get an at least monochrome video output with 2 colors, but defining black and white as colors, some can argue they are not colors, they are a mixture or an absence of those. And we will have in Raspberry Pi Pico that's driving in VGA output with a VGA base and also a DVI output with a DVI sock. That's the hardware we are using today. So from the performance class, fully different things. Yeah, a small 60 megahertz AVR and a 133 megahertz dual core microcontroller. So different worlds, but really interesting things they can do with the amount of features are given. There was a question about the recording. I think that's already answered. There will be a recording available after the show. And yeah, so let's head on. Besides having hardware here, we are also giving hardware away. So giveaway of the day. we will give away one. You can see it in the side camera if you want to. We are giving away a combination of one Pimoroni VGA base. That's quite nice to get started with the Raspberry Pi Pico. And to that one also you get a Raspberry Pi Pico with header, so it's really just plug and play. And besides that, we are giving away 5 Raspberry Pi Pico W and 5 Raspberry Pi Pico. How to get there? In the click meeting, you will see a giveaway time. Click here, click on the link. If there is a keyword needed, you will find that in the chat. And yeah, I wish you the best, that you get what you like to get. So with the giveaways told, let's head on for the video. Yeah, it started with Composite video, the yellowish connector, a single wire that has all the video information in it. Started as VBS in the English world, video blinking system, or BUS, Bild Auspass Synchron in the German. It's just monochrome, so it shows black, white, and more than 50 shades of gray in between. And it carries also synchronization information, so where the image starts and where the image stops. And yeah, usually you have this yellow RCA connector for it at that point. And I think there were written heavy books on composite video and how that stuff works.
Oh yeah, that those yellow connectors, they look so simple. It's deceptively simple, but when you look at what they went through to create these systems, I mean, I've got this book here, which is like a Bible. It's like over 1,000 pages of television engineering. It's crazy. And even this one I got here it's a lot smaller, a lot thinner, but still there's a lot to go through in here. So rather than sit and read this 300-page book to you, I think, Mathias, you need to summarize this for us so we know how they came up with these standards.
Yep, let's have a short look at the presentation slides. So the signal itself, it's built to drive a tube ray monitor, a tele. And the easiest thing to have a tele working with a electron beam moving from one side to the other is line by line. So your image starts with a synchronization impulse on it that tells the tele, hey, time to go, get ready. You have then in the signal a black pouch, a black level reference, so that the tele knows where black really is. And after that, it starts pumping out the brightness levels just in a linear fashion. And with these levels, the intensity of the electronic beam was controlled. Really, really simple and really intended to be used with these cathode ray tubes, these televisions. And looking at the timing information, you see you're starting top left and going down bottom right. And if you look at a modern digital image, you will still find the first pixel at position 00 top left. So that's...
So the origin is different to how we learned in school, where the origin is bottom left.
Yep, so they start top left at that point, and then run around the screen line by line until they reach the end, and then they start again. And yeah, as you can see, it looks really simple. And if you're just going black and white, it sort of is. And after that, they decided, hey, color would be fine. What about color? And then it really becomes interesting. Because, you know, not like today, you invent one standard and everybody uses it. No. First, it needs to be backwards compatible with what we already had. So with the monochrome FBus or VBS. And from that on, as they needed the backward compatibility, they invented PAL, NTSC, and CCAM. So the main three. CCAM is a color system that uses frequency modulation and needs definitely more circuitry and triggery to get the color back. And Paul and NTSC also added trickery to the signal. Quadrature amplitude modulation is used in that signal, which makes it more complicated to generate with a microcontroller at that point. So we can look at the signal. You have on the left side the usual monochrome signal going from black to white. And you have on the right side an PAL encoded image going through the colors you see below. You have the intensity level like seen for the monochrome image, and on top of that, you will see that there is an amplitude modulation that's giving one part of the color information. And what you can't see here really good in the scope capture is there's also a phase shift going on that gives an additional component for the color. And with the luminance level and the other two components, you can recreate the given color in the signal. And they haven't used RGB. They have used the YUV color space. Have a look at the Elektor article. It's mentioned how that works and how to calculate from RGB forth and back. And it involves floating point mass, so not microcontroller friendly. But
so they didn't do the obvious thing, which I would have done lazily. They had black and white TV. They needed color. They could have done, okay, we need red, green, and blue, so we need triple the bandwidth. We will simultaneously broadcast the color signal for the color TVs and the black and white signal for the black and white TVs and phase that out gradually. But no, they decided to go engineering mission impossible and add the color to the black and white TV and still make it compatible with the original black and white TVs in the same bandwidth. That's pretty impressive for the time.
Yes, definitely. And I mean, for NTSC, also sometimes called is never the same color. If you had a small shift in the signal, your skin tone would get greenish on your palm trees. Your green palm trees would get pink and sort of that stuff. That's later on solved.
That's why NTSC TVs have that tint control and PAL TVs don't.
Yes, PAL has some trickery in it that makes at least that not visible to the eye. The picture will get less sharp, but yeah.
Or less saturated.
Yeah, but you have to pay another license. So, yeah, with that said, as already told, in the current January edition of Elektor, there is for this one also in the main article, you will find additional information on that. It could be easy, but isn't. So,
they wanted a challenge.
Yeah, sure. Let's go with the composite with AVR or Arduino. So the nice thing is, as we have seen, just getting black and white are just two levels to do. And with an AVR, that's quite simple. You just need to be able to create two different or three different levels of signal, blacker than black and white, and the right timing. And yeah, you can do NTSC with 640 by 480 visible pixels at almost at 60 Hertz. Or you can do PAL with 720 by 576 pixel at 50 Hertz. So those are both resolutions you can output, and you can generate that on the fly. So for every line you output, your CPU will put up the right informations to the I/O pins. And with the Arduino, the circuitry you need for that is really simple. It's just two resistors. It's one 1K and one 470 ohm resistor on the right pins. Connect it to your RCR jacket and put it to your monitor, and you will see an image output. There is a TV out library available. You have then the two colors. You can do 128 by 96 pixels default, and you will use the RAM inside the Arduino as a kind of frame buffer. So that's why you're limited in the pixel resolution. But if you look at the output, at the demo outputs, this is quite nice. So you already talked about the Space Invaders, and that's what we also have here, a fully working Space Invaders. And yeah, controlling that and not seeing where I hit.
That's
so
amazing.
this game is fully running on the AVR, just the two resistors and the joystick, of course. You need to control your chip a little bit. And that's just doable with the TV out library. So not much trickery, looks really nice, nicely animated. You have a set of few sprites that you write into the RAM, just pixel on, pixel off. I think that's a cool one. Links and stuff like that after the show in the slides. And we can also do Pong, so the real classic. Let's restart that. Takes a little. Also on the same video input. The AVR takes a little until, yeah.
So this is running on that one-wire video output interface on the Arduino?
Yes. Yes, if we can go to the, yeah.
Wow.
So
well, that's a far cry from this rig.
Yeah, I said circuitry and some more hints on the AVR and video output you can find in the article. There's a lot more going on. Also, some guys managed it with a lot of more trickery to get PAL color output. So, but that's a different story and not for today. And yeah, I think that's that. If you want to give your kids something to do, a little bit of Pong, a little bit of Space Invaders, it's not much parts that you need, just the AVR, a few resistors, a few buttons, and you're good to go. Ready is your game system. And they also did Tetris on that one.
I'd like to see their face when you give them that when the neighbors get the PS5.
Yeah. Depends. It really depends. So, yeah, then, oh, we have an hello from Antarctica. So that's maybe nice to see. And yeah, let's move on. I mean, monochrome color and just a few pixels, as you can see, you can do really interesting stuff. And yeah, it takes a lot of less resources. Oh, let's move that back to Pong, and not Pong, Space Invaders. So if we move over to the camera of that one, you can see you can do animations and stuff like this, and it's not looking bad. I mean, during my childhood,
the resolution was
128 by 96 pixel.
Okay, interesting what you can do with that.
Yeah,
in
that's
fact, this one here that I showed earlier, that's 256 by 192, so it's double the horizontal and double the vertical, and yet you have a perfectly playable example over there.
Yeah, so it's quite nice with the right kind of trickery what you can do and with the right amount of imagination at that point. And I think the pixel artist in this respect, doing graphic styles that's enjoyable and not just horrible, I think that's a real skill of itself to do. But for those micros, it was what we had back in the days.
Mm-hmm.
And
no
today it's,
here.
I mean, it's coming back. You have today still on modern systems pixel art style games, and they have their own charm developed over the time. Have a few more pixels and colors nowadays, but still really enjoyable. And yeah, after that, the next thing for graphics, besides composite video, which was still limited, moving on, getting the right slide. The next innovation was VGA. So colorful video for the IBM PC. And that has lasted for a few decades. So 1978, introduced by IBM, just requiring 5 signals, horizontal vertical sync, 0 to 5 volt. You can also draw, it's defined with 2.5 volt is a high signal, so you can drive it even with 3.3 volt microcontrollers. H-sync and V-sync, and red, blue, and green ranging from 0 to 0.7 volt analog. for
so
the
voltages are again 0.7 volts from black to white, just like they are with composite, except that with composite, you've got the sync is everything below 0.3 volts,
yeah.
and full is 1 volt. So you still got the 0.7 volt peak to peak, but there's no synchronization, so they've moved that down.
Yeah.
And the synchronization is TTL level, but you say it works on 3.3 volts, which is great because that's often an interfacing challenge.
Yeah, so definitely no conversation needed at that point. So that makes it really easy to drive a VGA output, even with modern MCUs. And as you can see, the pixel clock you need to output is 25.175 megahertz, so 640 by 480 at 60 hertz. And back in the days, it was still at that point quite of a frequency to generate, but easy doable. They did it in full ASICs, or sort of ASICs, with a little bit of digital trickery. And yeah, if your microcontroller can output something around that frequency or a little bit less, you could get a VGA signal. You can, or as long as you are able to generate a valid H and V sync, to say it correctly. And the interesting about VGA, it's still invented with CRTs in mind. So it's built up to have array travel time. You have the horizontal sync pulse, black pouch. You have invisible lines to give the array the ability to move to the right spot. Then you have a visible area. Then you still shut it down to give the array the chance to go back to the starting position of the next line. And you can still see that it's still made for CRT monitors.
It's interesting that they chose the 525 line standard like NTSC, even though it's not interlaced, so it uses a lot more bandwidth.
Yes, but at the end, if you have an NTSC color monitor, NTSC color tube, you can use the same tube with a lot of less circuitry around it, with simpler circuitry, and that's it. So it's basically a color TV without the TV logic and just more or less directly driving the tube itself at a little bit higher frequency. But yeah, that's where it started. So you can see the tele standard followed us a long, long way. But for the MCU, it's quite easy to drive that. And
it's followed us, and you're not going to let it go.
Yeah. Well, most of the MCUs don't have a digital to analog converter internally that's fast enough to drive those signals. But with a pair of resistors, you can easily overcome that. So an R2R DAC or a binary white DAC will do the trick. The Raspberry Pi guys used on their reference implementation for VGA the binary white DAC approach, and others use the R2R DAC approach. Super simple, just a few I/O pins. You could even do it with an AVR. There were people that overclocked the AVR to 32 megahertz to get VGA output out of that. But it's not within spec, at least for the AVR. Yeah, and during the experimenting, there was the need, hey, I have a microcontroller, I have some pins. So a small mini circuit on the, you can see on the camera here, has been done that just takes 1 to 8-bit per color RGB input, switchable, and have a nice VGA output you can hook up to an evaluation board of your choice. Runs with 3.3 volt and is available on Elektor Labs. So you can get your schematics and build it yourself. It's 0805, so it's hand doable. And yeah, it's a nice way so that you don't have to put every time the right resistors in the right place on a breadboard and maybe something falls apart, and you know the deal at that point. Yeah, you can find it on the Elektor link seen here in the slide, and may also check out a few other Elektor Labs projects while you are there. So yeah, and well, so speaking of that, if you do VGA, one chip you may have at home is the ESP32, and that can do VGA output and really nice. You have the FabGL or the ESP32 lib for VGA output. You can look that up. The link is in the Elektor article. Up to 14-bit color, 640 by 480, or 320 by 240 pixels, depending on how much your RAM have left, or how much colors you like to use. And yeah, the nice trickery about that on the ESP32, they misuse or use the I2S peripheral, the sound peripheral, to output the video data. So less CPU intervention is needed to get data shifted out. It's a quite nice approach. And if you look, the people who built this library banged their heads around some limitations on the ESP32. Yeah.
So extra hardware for that? What do you need to interface to VGA?
Just in DAC, just a set of resistors. So
wow.
Just something like this, jumper wires, let it go, runs. And with the FabGL, it's not just an library to put out graphics, it's also doing audio, sprites collision, generating graphics on the fly, UI elements, and a lot more. So
that's amazing.
Yeah, it's really, 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 really nice. And also with the ESP32 lib, that's doing full color video, so 200 by 400 pixel resolution. So that's really, really nice.
It's not April 1st, so you must be serious.
Hmm?
You must be serious if not April the 1st. At that resolution in full color.
Yeah, I mean, the limit at that point is the internal RAM of the ESP32, because they are using, in the first step, a frame buffer. There's also erasing the beam approach. And that's something also the Pico is doing. We will talk about that a little bit later. And with erasing the beam approach, you can do a lot more interesting things with more limited RAM. So let's move on. And I think the Pico is the interesting one here. It's a lot cheaper than the ESP32. And yeah, if you look at it, the chip, or the whole board itself is €5. You need also a DAC. Does 320 by 240 pixel with up to 16-bit color, which is definitely a lot. You can have multiple graphic layers, and you can do a affine transformation on Mode 7 graphics. And this affine transformation, it's a pseudo 3D effect. If you, for example, want to create a racetrack, that's what it's used for. So older games, if you may remember, like F-Zero or Mario Kart, are using that heavily to generate the racetracks. And this, what you can see here, this Raspberry Pi, we will see the live demo. That's also composed of small graphic elements. So it's really powerful at that point. And it can, or there's more to that. So we have here some images of what the Raspberry Pi Pico can generate on the VGA output. There are multiple libraries. And if you do the math, the top image, the two castles you can see, that's a 640 by 480 graphics output with 8-bit color, moving elements, transparency, all that stuff. And you wouldn't fit that into the RAM of the machine itself. So there is trickery involved. You can see the classic Pac-Man, you have scrolling demos, you have moving, even heads walking around at that point. And yeah, how do we get there? There are two main libraries you can use. It's the Pico VGA library. You find the GitHub link with examples for the Raspberry Pi Pico and sample schematics, or you can use the scan video library from the Raspberry Pi Foundation. Both produce video output. They are not, at least the Pico scan video itself is not fully polished to the extent the other library is. But it does its trickery, and what they can do is graphics from a frame buffer. And the interesting point is both this, the Raspberry, you can see there is a 320 by 240 image that's fully running out of the frame buffer of the Raspberry Pi from the RAM. The other one is a full-color 640 by 480 pixel image, and that shouldn't fit into the RAM of the machine. So if you do the math 60 by 2 bytes, you will get more RAM requirement than the machine has. And there's another trick that the Pico has, and that's streaming image data from the SPI flash to the controller outputs itself. And that's more the advanced stuff, but it's quite nice to see that it's possible.
Is that uncompressed image data? Because, for example, the Raspberry Pi, there's a lot of blue in the background. So
yes, run length encoding is also possible. And the PO state machines will do that. So you just deliver the run length encoding, the compressed image, and the PO state machines will decompress it for you. So that's really quite nice. You can have a look at how the frame buffer graphics works. It's you have a pixel array in RAM, you have a CPU that fetches the pixel arrays and then move it just to a set of buffers, line buffers. There's a DMA unit. We don't have time to go into detail for that one. And then you just tell the DMA unit, hey, there's a bunch of memory, please transport it from A to B. And in this case, from the RAM to the PO state machines that will generate your video signal. And from time to time, you have to update the DMA unit where to fetch it, where to fetch the next data. And that's quite interesting, and you don't need much processing power for that. And you have 2 cores, so just one core is doing the VGA stuff and moving data around, so there's plenty of power left. And the other thing is, if you look at these EBAN heads, and they're moving around, or if you look at this little sandcastle, they are 640 by 480, and there's another trickery involved, and that's tiles and sprites. So if you don't have enough RAM to do nice graphics, why don't draw them on the fly? And this works quite interesting and very similar to what the TI-99 did. You put small images like 16 by 16 pixels in RAM, and a lot of them, for example, 32. And then you just put another table entry where to put these little sprites or these little images on the screen, for example, in the middle left or wherever. And then at the point where you need to write one line of pixel data out, where the beam would run around, you will do it a little bit ahead of the beam.
This comes back to what Axel Röst asked about this racing the beam you were talking about.
Yes. You just generate just ahead of the beam the image data, compose it on the fly, line by line, and send it out. This means you have all the small little graphics around that, if composed in RAM, wouldn't fit. But then you can do multiply images or multiple sprites that form a background and put it in the right position. If they are repeating, they still look really, really nice. The CPU will prepare that, put it also in the line buffer, like fetching from RAM, just an image, and just need to do it, let it say, 8 or 16 lines ahead of the beam. And this lowers down your RAM requirements a lot to do so. There's sample code around for the Raspberry Pi Pico to do so, also for the ESP32. And with just a few kilobytes of RAM, you can do amazing stuff. And this is how the old machines did the trickery with the graphics. They didn't have megabytes of graphics inside. They just had, as you said, 16 kilobytes or even less, and could do amazing things, thanks to sprites and sprite manipulation and sprite trickery. And with the Pico, it's the same to do so. And besides the VGA and stuff, we have also the digital video interface that's around. There is no analog output any longer, just digital pixel transmissions, red, blue, green separated, and also just a clock line. And they are running around 252 megahertz for the lowest resolution, 640 by 480, 24 bits color per pixel, 8 bits per color. And yeah, it uses also an transfer minimized signal encoding, which is not that easy to generate. But if you overclock your Raspberry Pi to 252 megahertz and use the POs in some trickery, you will be able to output a digital video stream with just that 1 bit output that you need per clock cycle of this chip. And that works, and that's how the DVI SoC will do its work, or why the DVI SoC works. So you have one core set aside that will just do the on-the-fly pixel and data encoding for the DVI output.
And you've put there that it's HDMI shaped, so it uses an HDMI connector.
Yes.
But it's DVI. Is that for licensing reasons?
Yes. If you put, if you're just mentioning that it could be HDMI and that could be supporting audio, lawyers will be around you quite fast, quite soon. So it's a totally hell to call it something like HDMI. It's plain DVI in this point, and I have heard rumors and seen demos that somebody did insert audio into this output and make it DVI plus. So it's inserting audio into a DVI stream to let an HDMI-compatible system see it as audio and video stream as possible. That has been done. There's also sample code for the Raspberry Pi Pico around. But for licensing reasons, this is just plain DVI. This is just plain video output. It has an HDMI-shaped connector. So
yeah, HDMI, for legal reasons, is a huge D-shaped magnetic interface. HDMI.
Yeah.
It stands for, in this case, a huge D-shaped miniature interface, right?
Yeah, sort of. Nevertheless, we got a sort of question about raising the beam. The raising the beam approach, we got back to that a little later, if talking about sprites and sprite stuff with the image creation. So yeah, raising the beam means you have to output a data stream to get the monitor displaying something. You can't stop. You have to push a constant amount of data or constant amount of signals in a timely manner out of the system that the display will be able to show something. I mean, you couldn't. I mean, a monitor was expecting the control signals for the beam at a certain in a certain timing, and this has been not changed. And the raising the beam approach is at that point, hey, I have graphics data, and I don't store a whole image in my system. I just have enough logic that I can create with the informations where something should be on the fly a new image 16 or 30 times a second. So you just say where things should be. We will see that with a sprite sample. I think that makes that a little bit clearer. Also, first back to the DVI. So there is a library for the Pico that has the DVI output, has all the things set up, has all that stuff optimized. That's C, currently not in the Arduino framework integrated, and comes with a sprite library. So raising the beam is done. And let's have a look at a few demos for the moment. I need to disconnect and connect stuff. And that's where things get interesting. Live demonstration was changing things live. What could go wrong?
Besides my squeaky seat,
yes,
we're good.
So let's see if that's working. Yes, it is. So what you see here is a video generated on the fly on the Raspberry Pi Pico with 640 by 480 and a lot of moving around people. And the Pico has definitely not enough RAM to store that. So every time it needs to put out a new image, it starts on line 1 and looking up where items should be and putting together pixel by pixel, line by line, and shifting that out a little bit ahead of the required output.
And that's coming from that little thing.
That's coming from that little thing, or yeah, just a few resistors and an HDMI-shaped DVI output later. That's
wow.
So you can see the colleagues from MacPi have a small article on that. I need to see if I can move that. Pulling on cables where you don't know when they end is good. So you can see it's just a plain Pico with the added DVI header producing that image on the fly. Running at 252 megahertz and utilizing for the image output both cores, quite heavy.
Well, that's certainly very impressive as a novelty, but have you seen any practical use for them? Maybe in airport time displays or something, because these boards are so cheap.
No, I haven't seen them used as pure graphic outputs for the moment. There are ideas to use them as a graphics coprocessor, for example, on a C64, but haven't seen something fully done yet. So that's to be determined. The other thing I talked about is the Mode 7 graphics. So if we have a look here, you can see this pseudo 3D effect shape. And if you now imagine this is a racing game, you can see where it goes. And this is just having the Raspberry Pi Pico image as a tile map. And talking of that, let's talk about what are tile maps, tiles, and how the moving people around are at least composed to give a rough idea. What you can see is a so-called tile map. So you have these little tiles, 16 by 16 pixel, and you will just tell the software where to put them. So you have a map, a tile map, how they are located, and it's looking like a mosaic on a wall, basically. And if they are all nicely combined together, you have the background, and then you can say, hey, I need, for example, a walking character in the front. And you can have then sprites that have a transparency information to them, and then put them for one frame in a certain position. And then after the frame is done, update the sprite position or sprites position so that you get the illusion of, for example, a walking person around. And this is also how the old games on an NES or SNES are done, or even other similar systems. The C64 in a not that advanced technical fashion, but also doing the same trickery with sprites. And you can do amazing effects.
Do you know if the C64 had hardware sprites?
Yes, as far as I understood, yes.
Because the something Texas Instruments had 32 hardware sprites, but single color only, so nothing as pretty as these that you're showing here.
I mean, the first system that used something like sprites was the Atari 2600 player missile or pedal ball image. They didn't call it sprites back in the day, and you had two or eight of them with a little bit of trickery. And yeah, it advanced really, really far, at least for the 2D effects. And I think the latest evolution on sprite engines was the Neo Geo, the arcade machines. Yeah.
Well, Ari has a question in the chat room. He wants to know the obvious. Can it play Doom? I'm thinking no.
The RP2040 can play Doom.
It can?
It can, yes. I haven't prepared that, to be honest. But it can play Doom, and it can play Doom multiplayer.
How mapping was impressive.
Yeah. So it can do. Also, the MacPy colleagues had an article on that. So there's source code for Doom that you can put on the Raspberry Pi Pico. It will overclock the system a little bit, and depending on when you bought them and which flash chip iteration you have, it may work or may not work.
Do you need the HDMI sock or DVI sock? Sorry.
You need some kind of VGA output. So they are driving VGA, not DVI. Because
okay, well, I've got this waiting, doing nothing. I'm going to try that then.
For the DVI, with the Sprite library, it's quite easy to get started for digital video output. For which, as said, Doom, you need all the processing power for even, to get the VGA running. So there's no core to spare for the DVI output. That's sadly for that, but you could do couple two Raspberry Pi Picos, one just as the graphics engine and one for the rest of the logic. So nobody stops you from doing that. So the demos we saw, we have the walker scene. That's the moving people around, and we have seen also the pseudo 3D effect of RP2040. And this has been, I think there's one game out there for the Pimoroni game system based on the RP2040, the handheld, that uses this effect to create a Mario Kart style race game. It's quite nice. Documentation is around, links and all the interesting stuff you will find in the current Elektor magazine and the main article, and in the upcoming issue will be a second part that goes more with the VGA and DVI stuff. And also all the nice links and trickery involved will be found in those articles. Yeah, and from the time frame, as sorry as I am, but we are coming to an end, sort of. So that was it for this webinar. So more showing the moving pixels that we couldn't do in print. Well, with the current print technology, we can't do moving pixels. And yeah, so if you want to start, I mean, the RP2040 is really a nice one to go with. And if you like to know more about it, have a look at the Elektor magazine, the current issue and the upcoming. Have a look at Elektor Labs for interesting projects around video generation and also other stuff. And if you like to get informed about new webinars, maybe free articles, may register to the eSign, the Elektor newsletter. And if you like to get more webinars, up there in ClickMeeting, you will see a register page for the upcoming MicroPython on Arduino webinar with our colleague Stuart. So may look over to those also and register for that one. That's on the 9th of March. So I think it will be quite interesting. And yeah, for me, that would be the end. If you have any questions, now would be the time to do so.
Some questions. I'd have to say, Matthias, that is an excellent article series that you did. In fact, it was so comprehensive that it was long enough to be a book, and you had to break it up into a couple of issues. So I would recommend to anyone watching to check out that series, starting with the January issue.
Yeah, definitely. Yeah, any questions from the audience?
I'll just put a preview up in the meantime. What was the keyword?
Video team. If you could put that again in the chat, the keyword for the giveaway. That was Pixel Artist, but seeing that written and have the ability just to copy and paste it, I think would be a lot easier for the people.
Yeah, code word Pixel Artist. Let me type it.
Yeah, it's in the chat. Marketing did put it in the chat. Yeah.
And
so
like if you are going to use the code word, hope you win.
You can review this webinar. It will be a recording available. Have a look at the Elektor YouTube channel. There is, for this library, the Pico, ESP Pico DVI library. There's a software library, and for C, C++ around that will do all the sprite trickery for you. And also for the VGA output, you have the same libraries, or sort of libraries, that will do sprite trickery. And as for the VGA output, there are a few more POs freed up. You have also the ability to do even more trickery, like multiple layers, sprites on sprites, and stuff like that. So even more graphical stuff you can do.
Great. I see a few questions coming up about CCAM. Are you aware of any CCAM projects that Elektor did in the past? Obviously from French audience.
CCAM, I'm not aware of that. It's the problem is CCAM had its main propagation, I think, in France and also in the Eastern countries. No, did not do projects about it. I mean, to be honest, in the current days, or in the current modern days, with full digital video transmissions, the formats or format difference are more or less like on the digital resolution and no longer on the encoding itself at that point. So
yeah, the Texas Instruments came out in NTSC in America, but for Europe, they released a version that output the Y, U, and V, the luminance and color difference signals. So theoretically, you could encode it to any signal, but I never saw anyone do CCAM. It was just too complicated. I think it was easier for them to turn it into RGB for the Scott Peritel systems in France.
Yeah, I mean, CCAM has this yeah. I mean, to encode and at least to decode a CCAM color signal, you have to store a full line of color information to get the color out of that, because you need the color information of the previous line to get the color of the current line. They had their own advantages and disadvantages at that point.
Yeah, système électronique collé avec mémoire, if I'm not correct. Avec mémoire being the keywords.
Yeah. The most important things in French are at the end of the word. So, and yeah, no, so CCAM mostly not. So most what you will find is Poland and NTSC as this is the main used regions, or the regions I mean, the interesting part is if you have at a later point in a CCAM tele set, it would also do PAL at some point, especially for some regions in Africa and the Middle East. You had this multi-norm systems already. So
yeah, it's crazy what we came from and crazy what engineering they went through. It's almost like they wanted to fail, but they pulled it off somehow. I mean, I can understand the digital stuff, racing the beam and that, but with analog, so much can go wrong, and they got it right.
Yeah, I mean, it worked for a long period of time, and at least you get, if you want to get some signal, you would be able to at least imagine that there's something in the white snowy one you saw on the telly, and with the digital one, it's working or not working. But in modern days, internet connectivity and streaming, who needs color formats any longer?
Yes, my TV in the 80s never used to buffer.
I know, that was one of the small advantages of linear television.
Yeah.
But you were not able to choose what you would like to view at the point when you would like to view it.
Yes, I remember when they started experimenting with video on demand and cable systems in America. They would have like 500 VCRs lined up. You would sit at home with your box and select your movie, and someone would go and put the tape in up in the cable station up on the hill. Hilarious.
I mean, I saw that in Germany, they just had a few channels just time shifted, transmitting the same stuff 1 hour later, 2 hours later, 3 hours later. So
Yeah, we had that here in South Africa too. Anyway, thanks a lot for the interesting information, Mathias. It looks like the chat enjoyed the stream.
Yep. And
this is
yeah,
just a taste.
Guys, and if you're still here and want to have a deeper look in that, may write to the Elektor support team. Maybe you will get a kind of academic course on doing graphics on a microcontroller. So customer feedback and customer requests will help to form even a better webinar and academy experience.
Yeah.
And yeah.
We might not do CCAM, but other things are possible.
Then, Brian, until next time.
Tschüss, arrivederci.